Well, welcome everyone, both those of you who are here in the room in person and those of you who are online. Thank you for joining us for the next in our Frisch Center for Autism and Innovation Faculty Fellows Salon series. We had the inaugural one of these back in December, hosted by the Owen School of Management. And this month, we're doing it in partnership with the Department of Computer Science here in the School of Engineering. My name is Kayvon Stassen. I'm the Stevenson Professor of Physics and Astronomy and a Professor of Computer Science. And I'm also the Director of the Frisch Center for Autism and Innovation in the School of Engineering. And the purpose of this, what we hope will be a regular and roughly monthly, what we're calling Salon series, is really to feature the work of the faculty fellows and affiliates who have chosen to be members of the Frisch Center, to participate in the Frisch Center's work. And as you'll see today from Tyler Derr's presentation, what we really want, what we really hope with the Salon series is that we all have an opportunity to see what are sometimes a kind of surprising, tangential connections to autism, neurodiversity. Some of the speakers that we will feature in this series work very, very directly on research having to do with autism or neurodiversity. In other cases, people do research that's tangential, but perhaps inspired by autism and neurodiversity. So we really wanted to bring out all this whole broad diversity of research that we're all working on, and hopefully encourage you all, if you're not already connected to the Frisch Center, to consider joining us, to consider applying to be a faculty fellow or affiliate if that interests you as well. So lastly, let me just tell you a little bit about the Frisch Center, which is a center of the School of Engineering. Our tagline is Engineering Technologies and Transforming the Workplace, inspired by neurodiversity. The Frisch Center seeks to bring together engineers, business scholars, and disabilities researchers with experts in neuroscience and education to understand, maximize, and promote neurodiverse talent from a strengths-based as opposed to deficit-based understanding of autism and neurodiversity. The center sees opportunities for innovation in technology and in workplace practices. And so with that, I'm going to turn it over to our presenter for this time, Tyler Derr, who's an assistant professor in computer science and a recent recipient of the prestigious Career Award from the National Science Foundation. As a National Science Board member, I'm especially proud to have a Frisch Center faculty fellow receiving such a prestigious honor. And Tyler's going to tell us about his work on network science for social good. Tyler, thank you. Welcome.
Thank you. Hello, everyone. Thank you. Okay, so I want to start out by briefly, I guess, introducing myself and the Network and Data Science Lab. So, just a little bit. As you can see, I joined here in fall of 2020. I am affiliated with the Data Science Institute and the Frisch Center for Autism Innovation, assistant professor in the computer science department. And generally our research in the Network and Data Science Lab falls within these categories. So I just use the mouse. Within kind of deep learning architectures, specifically on network structured data, looking at responsible and trustworthy AI. So these are areas such as model explainability, fairness, and then also heavily in the social network analysis and recommender systems domain. And so this is in the areas where taking some kind of social network, trying to understand different properties about them, forecasting, and recommender systems we'll kind of get to later in the presentation. And then we also focus a lot on interdisciplinary social good applications. So these are essentially taking our efforts in the deep learning on graphs, social network analysis, and the rest towards directions such as drug discovery, looking at neurodiversity, autism, kind of in online communities, looking at education, how can we improve these different types of areas, leveraging the techniques that we're developing in network science. So I guess the first thing to kind of say is why networks? And the reason for this is that actually a lot of the data that we have today is highly connected. So whether this is connected through things like data fusion, looking at the Internet of Things, power grids, knowledge graphs representing different entities and how they're related together, or this could also be traditional types of social networks. In the biomedical domain, this could be taking fMRI data and converting this into functional graphs. It could be connecting diseases with proteins, etc. And so the outline of the talk is basically going to follow this kind of structure, where first having some background into the research, talking about constructing graphs, graph analysis, making predictions on graphs, and then talking about some future directions. So jumping into the background, a traditional type of view of data is usually as a set of objects, or if thinking as kind of tabular data, some kind of table where we have different entities and they have different features, qualities about them. Whereas compared with network data, this is generally seen as a set of objects, but we also have interactions or links, edges connecting them. And so the benefit of network science is that it provides this general universal language that spreads across multiple domains that want to study complex systems in some kind of unified way. And so here we'll kind of use network and graph interchangeably when we're talking about these objects, kind of nodes and vertices. And as I said, these interactions are kind of the links and the edges. So the general topics here kind of fall within trying to model these networks. So for example, looking at their different types of properties and saying, how does this compare against something that's inherently random or approaching random? We can also have different network types of measures. So PageRank is a classic example here of network centrality, where this is used by the Google search engine to rank web pages. Another type of problem is looking at spreading on networks. So this is in the directions of something like trying to model information diffusion, misinformation, the spread of a virus during a pandemic. All of this is thought of as something spreading across a network. We also have link analysis and predictions. So as a graph is evolving over time, thinking about how we can forecast these types of predictions. So think of Netflix knowing what movie you want to watch next. And then we also have classification and clustering, where a classic example of something like classification on a network would be you might have the known political affiliation of some users in a social network, but you don't have the affiliation of the majority of users. And if you want to target advertisement dollars, maybe you want to try to first classify these online users so that you can then kind of spend your money in the best way you can. But so all of these are kinds of general network science types of topics, but specifically we're going to focus a little bit more on this kind of classification, clustering, and link analysis seen over here on the right. So the main problems when thinking about machine learning or artificial intelligence on graphs can be kind of compartmentalized into a few different types of classical problems. So one is that of no classification. And no classification can either only look at the topological structure, or we could have different features or qualities about this data. So if we think about a financial transaction network, we can know the usernames, we can know when they created their account, the amount that's being transferred, and we could use this for something like fraud detection on that type of network, or traffic prediction, predicting social influence, detecting extremists, critical nodes and disaster response. A lot of different types of problems can be modeled as a no classification problem. In comparison, sometimes we might not want to classify individual entities within a graph, but look at the entire graph and make some kind of prediction. And so here, this could be something like looking at a molecular graph and looking at some kind of drug property or material property about this structure. People have used this for network intrusion, malware detection, suicide ideation prediction, lots of different types of problems that can be modeled as an individual graph and then making a prediction about this entire structure. And the last direction is that of relation predictions. And so the two common ways of looking at this are either predicting something about an existing relationship. So in a social network, predicting, is this a close kind of best friend, or is this just an acquaintance? Or is this someone that you like online or you dislike online? And some others are predicting new types of relationships. So within a knowledge graph completion or expansion is taking some kind of known structure and trying to infer additional knowledge by filling in the gaps. Or something like a recommender system, making these predictions, new friends, new movies to watch. And so with this in mind, the one thing that I want to kind of highlight here is that while most of AI has focused on this model-centric type of perspective, where this is developing new deep learning architectures, new loss functions, hyperparameter tuning, but there's also this data-centric AI. And so in data-centric AI, this can be thought of feature engineering, confidence learning to identify poorly labeled data, and then how we can construct our data set, basically looking for the best way to encode our data to get better real-world predictions, as compared to the model-centric is usually thought of as somehow more of a benchmarking. You have a data set, you want to find the best model given that fixed data. And so this is inspired by an XKCD from a intro to data-centric AI course at MIT, where they say, we realized our data is flawed. So the good thing would be to use data-centric AI to fix the problem. Bad thing, throw it away, start again. And of course, you get people that might just train the model anyway. And so with this in mind, kind of wanting to step forward into then saying, well, what are these graphs that we'd be looking at? Sometimes they're natural. It's a social network. We could say these people follow each other. They have connections. But other times we might actually need to construct this topological data. And so one example here is within graphs for recommender systems. So here we have Homer Simpson, and I guess he buys a lot of Duff beer. And so we might want to make some kind of recommendation. And to do this, we want to kind of understand this concept of similarity. So what products would be similar to something that Homer is already purchasing? So for example, this t-shirt. And one way to look at this is then if we construct a graph of all of these individuals in this kind of global data set and all of the products, that we could then see how they interact. And so for example, if we see that John has recently purchased this ice cream, and both Amy and Tim purchased that ice cream and this other dessert at the top, then we might want to recommend that dessert on the top to John as something to eat next. And of course, this has been extended beyond this kind of simple graph structure, where you could think of something like a Facebook marketplace, where you also have these social dynamics, not just the interactions from users to products, but also their individual friendships. We can have a knowledge graph encoding who are the actors in this movie, who's the director, a lot of different types of problems. And so one thing that we've done there is looked at recommender systems where we have this kind of outlier or noisy data. And so here's an example of Bob, where Bob's this electronics lover, but maybe they bought a children's book for their niece's birthday, seen down here on the bottom. And somehow this children's book really doesn't meet the traditional purchasing behavior of Bob. And so with this kind of outlier in mind, that this work that we introduced looks at how we can refine this graph structure based on this knowledge where not all of the data is going to be perfect. We're going to have outliers, and how can we reweight or adjust this graph structure? Another related problem within the recommender space would be, well, what happens if a user doesn't even log in? That they're just searching and browsing and they're clicking on different items? Well, we still want to be able to predict what they're going to interact with next to hopefully get them to continue making purchases on the platform. And so based on some historical shopping data, some data fusion with global information, we can construct a knowledge graph about how all of these products interact with each other, so that then when making this next kind of item prediction, what would they want to see or add to their cart next? We can do this based on this constructed knowledge graph. So another direction somehow related in that e-commerce type of setting is in the fintech world. And so you can also take historical stock market data and represent this as hypergraphs. And so hypergraphs are an extension of basic graphs where the entities are not just linked pairwise, but within sets. So for example, here, we can have different subsidiaries, we could have different industries. And for example, here, this travel industry, if we make these connections between them, but then historically things tend to fluctuate within their industry or within related corporations. So we've looked at some things like market prediction, portfolio optimization within this direction, coming from a graph-based perspective as compared to just treating it as basic time series data. Kind of switching to the biomedical direction, more recently, we've looked at some graphs for neuroimaging. And so within the neuroimaging domain, it typically starts out with having this 4D functional fMRI data. And typically, we want to make some kind of prediction here, or a prediction to develop a deeper understanding about the underlying structure. And so we had done a data-centric approach by looking at different ways that we can take this 4D fMRI data into different types of graphs. Are they static? Are they very dense, having lots of edges, not so many edges? Are these regions that are being grouped together, large regions, small regions? And what we basically discovered is that kind of across this, the columns are different types of graph neural networks. And actually, it doesn't vary too much of if you change from one model to the other. What really varies within this type of framework is how you encode the system as the graph. So the key insight is that larger, sparser graphs that use a certain type of correlation features end up performing better. So for example, across this entire row, if we have 100 regions in the brain, on average it's getting 67% accuracy here, but yet if we increase the size to 1,000 regions of interest or more fine-grained ways of splitting this up, we get much better performance as compared to just developing a new type of deep learning architecture. Similarly, graphs looking at within the healthcare domain, so taking electronic healthcare records, extracting out clinician workflows, and then taking these workflows, putting them together into a large kind of global interaction graph, how different types of tasks interact with each other. And in collaboration with VUMC here, unfortunately, we actually ended up seeing some differences based on white versus non-white patients, that apparently their clinician workflows are not the same. What that exactly encodes, we're not sure yet, but this could be used for identifying these inconsistencies, bottlenecks within the system. And this is just a visualization of that type of graph structure. And the last one that I want to highlight here in this kind of biomedical domain is that of molecular graph representations. So taking some kind of molecular structure, it can either be represented as a 2D or even as a 3-dimensional graph according to the underlying structure. And one type of problem that we might want to do here is that of looking for novel drugs for a given disease. And to do that, the drug discovery pipeline looks at taking a large kind of chemical library, passing them through a high throughput screening equipment, and maybe out of 100,000 that get tested, far less than 1% are actually seen as a potential active small molecule. And that inherently creates a very imbalanced labeled data set. So then when passing that labeled data over into the graph machine learning pipeline, we need to come up with ways, how can we handle this type of data imbalance to make use of this high throughput screening data? So I'll come back to that one, but kind of wanting to shift gears and thinking about, well, we've talked now about having data, constructing that data as graphs, but how do we then analyze these and try to uncover new types of knowledge from these data sets? So network analysis within political science, one thing that we've looked at in the past here is, well, in the past, people used to get their information on being kind of well-informed, good citizens to make their votes just based on kind of this TV, radio, newspaper, this kind of unilateral news consumption, that people just consumed what they were told. But more recently, with online social media, is this kind of new player of how individuals not only just consume the information, but they engage in discourse online. And even then, the question kind of comes up, how is this kind of going back and forth? Is it that mainstream media is driving the communication and what people are talking about online when it comes to different types of political agendas or candidates? Or is it that what's happening on social media is driving what these mainstream news outlets are talking about? And so in a previous work, we had looked at the 2020 presidential primaries and wanted to analyze this type of relationship. One kind of interesting finding is that we discovered a lot of topic mismatch. And what I mean by topic mismatch is here we can see a candidate, and according to what they're saying on their own social media, they might be talking about immigration and climate change. But then what are the main things that the mainstream media are talking about this candidate? Gun control and criminal justice, which somehow deviate from the main points that they want to emphasize. And then if we look at all of social media, most of the people online are also talking about gun control, but also immigration, which aligned with this candidate's topics of interest. So we had a lot more interesting findings here, but this is just one where the social network analysis can help us uncover deeper things within certain domains, such as within the political science sphere. Another one within the social network analysis is looking at kind of understanding online communities and individual behaviors. So whether this is Twitter, Reddit, different types of platforms, what we might want to do is kind of better understand certain subpopulations in online communities. We could do things like better forecasting mental health troubles, and to kind of put into context the work that we had done here. So there was this Organization for Autism Research study in 2020, which basically asked about 1,000 people, do they prefer person-first language or identity-first language, where an example of identity-first would be autistic person as compared to person with autism. And over 80% of the respondents preferred identity-first language. And we can kind of dig a little bit further on that and say, well, who were these 1,072 respondents? Well, most of them were self-advocates, but they also had parents, kind of siblings and loved ones, educators, professionals, and kind of going in deeper and saying, well, not just their personal preference of what type of language they would prefer, but if they're going to make use of content, are they going to prefer content that uses what type of language? And here we can see that the self-advocates strongly agree that they prefer content using identity-first language. A larger set here also would say they agree, but very few say that they would disagree. And that disagree is actually growing from the actual individuals to their family members to the professionals and educators. And so it seems like there's some disconnect there. And so we wanted to kind of also investigate what's taking place online. And so some of our preliminary findings here from the Reddit data across a wide set of related subreddits, such as our autism, our neurodiversity, our autism parenting, was that kind of across the board, there was about 5 times more identity-first language as compared to person-first language. And so some future directions here, we want to kind of dig further to look at how does this adjust temporally? So when someone first joins these online communities, do they use a certain type of language and then they change over time? We could also look at, well, just as seen in this survey, between self-advocates and professionals, there's this discrepancy. Do we also see the same thing here, such as in autism parenting? And so these are all different ways that we can use social network analysis to kind of dig and uncover interesting and novel findings in this knowledge discovery type of research domain. So now with that in mind, looking at some problems related to predictions on graphs. And so when talking about predictions on graphs, a lot of the work that we had focused on is looking at kind of real world data quality types of challenges. And so the two that we'll talk about today are what happens when you have biased data or data that's imbalanced. So biased data, this could be inherently unbiased from the data collection. It could be historical laws that were enforced. And so if you collect data from that, maybe it was such as people getting loans or not at the bank, people getting out on bail, that inherently then if you collect historical data, the underlying labels could be biased or they could be imbalanced, such as in this drug discovery example. But there's a lot of other things here. You have limited labeled data, missing values, distribution shifts, and all of this kind of fits within this data mining machine learning realm of saying, well, garbage in, garbage out. And so we really want to focus on these types of problems. Because in the real world, we don't have perfect data, and we need to be aware of these kinds of things. So why fairness? Well, here are just some quick examples of fairness within education, healthcare, finance, and I thought this kind of summed it up pretty well of the research community within machine learning thinking about fairness. A decade ago, not too many papers were coming out around this topic, but then thankfully, a handful of years ago, people really started thinking about, well, this is a serious issue and we need dedicated efforts here. So the first thing that you might be thinking, well, what does it even mean to be fair? And so here's an example of a bunch of individuals. They're looking to get a job offer. And here we're just showing some kind of binary sensitive attribute, although not really representative of anything particular, just two different groups of people. And it can be extended into multiple groups, but just kind of for simplicity, thinking about a binary categorization. So in the top example, we can see two of the blue and two of the orange end up getting a job offer, where down below, four of the blue get job offers while the four orange don't. And so one definition here is that of statistical parity, which would say this probability of getting the job offer should be the same or roughly the same between these different groups of individuals, where we can definitely see that this would be inherently biased according to this type of definition of group level fairness. There are others, such as equal opportunity, which takes into consideration conditioned on the labels, but we can just think of this kind of one definition of fairness of statistical parity. People have the same opportunity of getting a job. And so one work that we had done in our group is kind of marrying this concept of fairness with that of model explainability. So model explanations are looking at why should I trust the model? When we make these predictions, what types of kind of confidence do we have within these predictions? And so kind of bridging this gap between fairness and explainability is looking at fair explanations. And so at a high level, a lot of the previous work was looking at result-oriented fairness of saying, we have this model, a lot of the times it's some kind of black box deep learning model, and we look at the outcomes and say, well, let's ensure that the outcomes are fair. But that's somehow not enough, because the procedure of how these predictions are being made are also important. And so if we can kind of open up this opaque box into the model and look at their explanations and then say, well, furthermore, we want their explanations to be fair as well. And so this was the one work which kind of led into a stream of work. And so also looking at fairness within online dating recommendations. So certainly online dating and dating applications are becoming more and more popular. There's this huge information overload, so many people using the platforms. Even if someone swipes as long as they can, the number of people are near endless. And so recommender systems are being used to try to filter individuals to the top of the stack that someone might be interested in. And previously, people have looked at things like, is there bias within online dating according to subscriptions, how much someone spends on the platform, their race, their gender, but previously no one had looked at sexual orientations. And so what we kind of initially studied and wanted to analyze is there any kind of disparity here of people of different sexual orientations are getting different quality partners recommended to them? And I guess when saying quality of partners, it would be shown someone that they would actually be interested in and, for example, swipe positively towards that individual. And we noticed indeed this is happening, and attributing some of this to quantity imbalance. There are more individuals that are heterosexual or leaning towards very heterosexual as compared to otherwise. There's also calibration imbalance. And so we introduced some framework there that could level out the playing field so that all individuals are getting fair recommendations to find those that they might want to partner. Extending this into fairness and diversity within recommender systems. In terms of diversity, an example here could be food recommendations. So some individuals prefer diverse sets of food. Some prefer only one specific type of cuisine. And if we think of this back in like a friend example or romantic partners, different individuals have either very specific interests or more broad types of interests. And what we uncovered, some key observations, is that actually users who have higher interest diversity tend to have lower recommendation performance. And so those that tend to only like one type of thing or one very specific thing, well, they're getting a lot better recommendations than the rest of us. And so how to kind of adjust within that framework. And the underlying solution is based on multiple embeddings, which visually here, these yellow squares showing what the recommended things would be. And for someone that has diverse interests, now we're able to capture that type of thing. And kind of the last thing related to fairness here is talking about this no classification. And so I mentioned within the no classification framework previously, we have this concept where some of these individuals have labels, some of them don't, and we would like to predict the label of certain types of individuals. So this can be seen as we're looking to predict, should someone be approved for a loan based on kind of transaction history? Are they going to be receiving bail or not based on their known associates and their personal history? And because we have this structure connecting different individuals or objects together, this can actually impact correlations within those features. And so we had developed a framework that would look at then saying, when trying to make a prediction for this center blue node, taking into consideration the context, which is some of the power of the graph machine learning, we want to do so in such a way that we're not injecting or keeping this bias within the data. And so now switching, I had mentioned wanting to talk about imbalanced data and also talk about fairness. And so within this graph machine learning, there's a lot of real world problems that fit within an imbalanced data distribution. So I'd already talked about drug discovery being far less than 1% being predicted as being active, but also when looking at things like brain scans, for example, roughly 2% of the population is estimated to be autistic. And so that's also a data imbalance. Fake news, thankfully, not everything online is fake news yet, although with large language models, it's easier and easier. So this percentage might be increasing. Same thing with malware detection on like Android Play Store and things like this. It's still maybe 1% of these systems. So if we're looking to make these classifications and identify these types of anomalies, we had introduced different ways to do this. So when thinking about the entire graph, we can upsample and look at these minorities a little bit more. We can augment them. We can somehow connect them together. And in doing so, we're able to get improved performance. And specifically for that drug discovery, we had looked at developing a molecular kernel graph neural network, which is based on some ideas coming from the chemistry domain, such as ensuring that chirality makes sense, kind of like left hand, right hand transposing on each other. And what we ended up then looking at is the system was also interpretable. So what types of these small components or molecular kernels are being discovered? One of them, the one shown here, actually aligns with a substructure that exists in many currently existing drugs. And so what it was looking to do was look for these kind of subcomponents within the molecule and then leverage that to make these predictions whether or not that small molecule would be particularly active in binding with the target protein. With imbalance, we've also looked at imbalance in node classification. Currently, we're looking at imbalance in edge classification. So in this kind of edge classification framework, where different types of relationships might exist more than others. And so when looking to kind of fill in these gaps, taking this in mind, not just according to the quantity, but also where they're located within this topological space, introduces a topological imbalance as well. And the last kind of related application is that of drug pair scoring. So we collaborated with AstraZeneca and Harvard Medical School to create this Chemical X, which is an open source library for drug pair scoring, where you can take two of them together and then try to make some kind of prediction between them. So yeah, all of these are some recent and ongoing directions within the group. And I guess I kind of want to keep some of that concise and focus on some of these future directions. And so when thinking about the future directions, the first one is thinking, well, I had said a molecule could be represented as a simple 2D or 3D structure, but there are more complicated types of topologies that could be used here, such as cellular complex, which can kind of dig a little bit further into saying, not only do we have these pairwise relationships, but we have rings, we have functional groups, and how can we better leverage these for improved predictions? Another kind of collaboration here within education is, so here we have individual students, and they're working within small groups, they're interacting with each other, and one way that we could encode that data is with temporal knowledge graphs. And so with a temporal knowledge graph, we can see one student is talking to another student, they're looking at papers, they're interacting with laptops, and this is constantly changing throughout time. And what we want to use this complex kind of network encoding for is to kind of dig at collaborative learning understanding. And so this data collection here at Vanderbilt, kind of local on laptops, there's audio between individuals, we know who's using them. We also have classroom cameras that are getting these global interactions. And kind of the goal would be when individual students are collaborating within a project, can we make these early detections or interventions through personalized recommendations, such as one student is asking a question and their partner is completely ignoring their questions and they're just saying whatever they want. And so kind of recommending them, maybe you might want to engage in that dialogue. Maybe one individual is using the laptop much longer than the other. And so to kind of improve these collaborative learning environments, we need a way to encode that data, such as these temporal knowledge graphs, and then making these predictions on how they're going to evolve, how they evolve towards likely outcomes associated with test performances at the end of the exercises, hopefully with this goal of helping them improve their collaborative learning and downstream test results. So a topic that's related to fairness and privacy more recently is this concept of the right to be forgotten. So a lot of people are creating accounts online, whether it's a Facebook account, an Amazon account, and they perform all kinds of behavioral actions within these platforms. They like things, they post things, but at some point they might want to be forgotten and say, I don't want my data being used within some kind of large prediction framework at that system. And so we had recently released a survey of kind of machine learning on graphs, and also one related to privacy attacks and preservations. So these are some directions that we're potentially looking to go into. And further on that, temporal knowledge graphs, somewhat inspired by this past summer, I had, I guess, spent the summer as a visiting fellow at the Air Force Research Lab, and they were pretty interested in temporal knowledge graphs and specifically how they change over time, because a knowledge graph isn't fixed. Things are changing in dynamic scenarios. We may want to unlearn certain things. What we thought was true is not. And so putting these up in some kind of framework that we can leverage rapidly changing temporal knowledge graphs is one thing of interest to our lab. Another one is looking at kind of data-driven workplace accommodations. And so greater than 80% of people on the autism spectrum tend to be underemployed or even unemployed. And trying to think of how we can leverage data learned from some of these pioneers in this space to leverage this big data of kind of what works, what doesn't work for individuals, what are their strengths, what are their needs, kind of what prior experiences do their teammates have, and thinking of how we can leverage this to then recommend either accommodations or training based on historical data at other locations. Yeah, and certainly taking into consideration data privacy, but yeah, and one that just recently started here is that of kind of some national security related network analysis. And so there's a history course here at Vanderbilt where they do a role play of the French Revolution. So the students are different individuals, such as the king or someone else, and they interact throughout the class using Slack. And so they're supposed to adhere to their role within the game. They communicate, and it's seen as kind of a proxy data set for some national security related problems, looking at major event detection. Can we forecast certain types of things based on communication, like when the revolution is going to happen, when certain types of decisions are going to be made, and as compared to some like authoritarian type of decision-making, a lot of the times there might be these collective or collaborative decisions that are taking place. And can we leverage the spreading on networks to think of social influence and information propagation so that we can forecast before the collective reaches their decision that they're going to do a certain thing. And the last one is looking at kind of the impacts of influence maximization online in this era of large language models. So one way to think of this is, well, because we have these large language models, now somehow everyone has a personalized social media assistant that they can use to take what they want to say it in a better way to perhaps get increased popularity. Or if you inject this concept of their local social neighborhood, those that are following them, their followers are followers. And if they really want something to go viral, how do they say it? In what way? At what time? That's one way that we could look at this problem. Another one is with political ad campaign maximization. So if you have a limited budget, you want to figure out who do we target? What do we say to maximize this influence? And so maybe something like a large billboard in downtown might not be the best way to maximize the impact for a given budget. And the last one, thinking about, well, adversaries might also be thinking about these types of frameworks. And if we can show that personalized misinformation can spread much more rapidly, if we encode these social network connectivities into large language models so that they can personalize the way that they're trying to spread misinformation, this opens up the door as just kind of a warning that what's to come, I guess, especially related with the upcoming election. And lastly, just a kind of shout out to those that might be interested. So here we have the machine learning seminar series at Vanderbilt, co-hosted with Professor Kalori. This is kind of the set we had from fall 2023. It's every week on a Monday. Some upcoming talks. We just had one today talking about actually large language model types of discussions and looking at data generation. So feel free to tune in if interested in machine learning. And just acknowledgements. Yeah, none of this would have been possible without the great effort of the Network and Data Science Lab, funding support, and a special thanks to the Frisch Center and Computer Science Department. So yeah, thank you all.
Well, thank you, Tyler. That was fantastic. And we have some folks here in the room and some folks online. I'm going to ask Jess online to help moderate or point us to any questions that have been posed online or help us coordinate
not right now, but I can keep an eye on it for you.
Okay, maybe I'll ask the first question if you don't mind. You certainly got my attention with one of the future directions around understanding sort of workplace accommodations and and supports for autistic people in the workplace. Could you maybe just elaborate a little bit on, like, if you were to, and maybe you've already given this some thought, but how would you design, right? Because through the Frisch Center, we have lots of connections to companies that are doing neurodiversity hiring initiatives. We're connected to some corporate programs that have now employed hundreds of autistic people in jobs, right? So, given that sort of potential data set, if you will, can you imagine how you might design some data collection, or what kind of data instruments would you design to kind of do that kind of what you were envisioning?
So I guess thinking of this data somehow as a general recommendation problem, where knowing certain individuals had certain accommodations provided to them at certain times, how the outcomes were changing throughout that time. So I guess it depends on if this data, so if the data encodes this temporal type of information, and if we can also have information based on some demographics of these individuals, or as what role they had, were they a computer programmer, different types of roles, and then thinking of, leveraging that historical data so that moving forward, kind of, we don't have to recreate the wheel, but leverage this prior knowledge.
Yeah, neat.
Yeah, somehow data-driven as compared to just heuristics and people's.
Yeah, so I mean, clearly there would have to be some robust data collection happening, right? Like the managers at the companies would have to be making sure that when some intervention or accommodation was provided, that was written down with a timestamp and all these other labels, right? Yeah.
Yeah, and I guess similarly, like that example of the Slack data, if having access to anonymized communication channels or emails within these companies, I think that could also provide a lot of insights into these behavioral dynamics.
Thank you. Any questions in the room here? Or Jess, were there anything in the chat, or is anybody raising their hand, or?
Not right now, but I've left it open.
Okay. Well, maybe we'll just we'll wait for just.
Oh, we do have one.
Yeah, good.
It's how can the integration of an LLM enhance the value of a data-centric AI system, and what are the specific benefits?
Could you repeat that one more time?
Of course. It is how can the integration of an LLM enhance the value of a data-centric AI system, and what specific benefits?
Okay. So one way that can enhance this is through data augmentations and data generation. And so
Oh, thank
there
you.
can be a lot of settings where there might be limited data about a given area of interest, where there might be certain types of entities or objects where less information is known. And so leveraging the large language model to kind of expand upon and create additional context based on kind of the world knowledge within the LLM. And so that can be seen as this kind of data set enhancement type of process.
There a follow-up to that or any other questions?
Thanks, Sally. Now just waiting on the chat, but no, I think that was answered really well. Thank you.
Well, I have learned in my teaching to always wait a few beeps before deciding that there's not another question. So we'll just wait a second. Okay, well, thank you all who.
Oh, there's another one.
Oh, is there one?
Yeah, you were
Oh,
okay.
good.
Gotta wait a bit. How do we make sure the data output is accurate as we adapt to the AI model?
So how do we make sure the output is correct within the AI model?
It says, how do we make sure that the data output is accurate?
I'm interpreting that to mean sort of how, what are the ways to make sure that, AI-driven models are putting out good, good information.
So that's a good question. And I mean, the typical type of framework of setting this up as holding out some data and saying that this data we're not going to look at. And then when we make these types of predictions to see how well those predictions we made align with the ground truth that was held out, it's kind of like a testing data set. There are other ways of looking at kind of uncertainty quantification to know when, even if we're making a prediction, is it with confidence or is it a prediction that's being made with less confidence? And so I'd say those are kind of like the two classic ways that this gets done. Great questions. Yeah.
Thank you. That was a great question. Thank you, Tyler. Great answer.
So with that, I think I will thank everyone here in person and online